for waiting up. So, yes, today I'm going to talk about defense against the dark arts, adversarial machine learning, and we'll take the cybersecurity aspect of it. So, before starting, who I am, so my name is Amit, and these are like the social handle names. And I have worked for Zomato as machine learning engineer for 2 years. Then I moved to Germany to work for Zalando. There I'm as a backend engineer. I'm also a data science mentor at the Ready School in Berlin. Yeah, that's me. Okay. So what is an adversarial example? So on the left you can see there is a clean image which is classified as corrective because it is a correct. It is a truck. Now we have a noise. We call it like a perturbation. So exactly it is not a noise. It is a kind of information. It's partly generated. So when you mix those two images, and the output is again a truck, right? It looks like a truck. So, but when we fed it to a trained neural network, it says it's an ostrich. So what does it mean? It means that the neural networks, it is not classifying the image as humans do, right? It's doing the job, yes, but this doesn't have the intuition that humans have for classification purposes. This is an adversarial example. This is another adversarial example. So what we have here, so on the left we have a washing machine, a washer, right? So which is currently classified as washer, right? So what we do, we take the photo of the washing machine and place it on the table, and we have an application that detects what is it. Again, it's a clean image, it's a washing machine, right? But it's printed on a piece of paper. I don't know if it's correct or not, it depends on the use case, right? Then again, we have generated some noise and added it to it. Now, you can see it is classified as not as washer, and this one as like a loudspeaker. Yeah. So this is another kind of adversarial example. Okay. Now we'll talk about how we create an adversarial example. So this is like a clean image of Macau, and this is again the noise, and this is how we are going to generate the noise. And again, it is classified as a bookcase. It is a bookcase, right? So what is this noise? What should we add to the clean image that we get an adversarial example? So, yes. So what is the intuition behind creating an adversarial example? So this is like the simplest classification problem, let's say we are assuming. So we have two classes, like a plus sign and a cross sign, and we have this hyperplane that divides the two classes. So the idea is, we have an example here, let's say this plus sign, right? What can we add to this plus sign as an input signal so that it can cross the boundary and come here while keeping its visual appearance the same? So that's the idea. So the idea, how do we move to this, like this information, how much noise or perturbation we have to add to the input image. So this is the idea behind generating an adversarial example. Okay. So what are those algorithms? So the first algorithm is fast gradient sign method. So this is one of the earliest examples that was used to generate an adversarial example. So what we do here, we have a clean image x, and we take the derivative of the loss function. So we have a loss function defined as j here, which is a parameter. It takes the parameter input image x and the label y, right? So this is kind of the gradient with respect to x. So the whole this thing, delta jx and y2. This gives us the gradient with respect to x. What we do, we just add it to the original image. What it in effect do, it moves the parameter, it moves the input image like from here to here to another class. So this is what the fast gradient sign method do. And there are like two more methods, defool and terminated. So I will just go to the defool. So this is another algorithm that does the same job, like putting this sample to this side. But the underlying algorithm is different. So what it does, so we always have a loss function. It draws a tangent, or kind of let's say linearizes the loss function and update the input image, tell it the classification, the attack model, classify the sample into wrong class. So this was default, and we have Carnegie's another algorithm which is known as Carnegie's attack. So it treats this task to bring it here as an optimization problem. So we have a constraint-based optimization problem here. The constraints are, it should be classified as a not the correct, any other classes but the correct, right? And and what else is the constraint? We should keep the disturbances, the noise we are adding to the original image minimum, so that the visual differences are not too much. Right? So this was Carnegie's attack. So these are involves a lot of mathematics, and they are cryptic things, and we often okay, how we are going to do it? It's really hard, right? Okay. Clever Hans. How many of you have already heard about this Clever Hans? Few. Okay. Okay. So first I will just tell about it. So Clever Hans, it's a Python library developed by Ian Goodfellow and some few members, and which is used to benchmark adversarial examples. So I will brief you about the story of Clever Hans. So Clever Hans was the name of a horse that learns to do some very basic arithmetic, and it got famous. So what it used to do, so when the owner of the horse asked him the question what is 2 plus 3 equal to, and he will just shows the finger 1, 2, 3, 4, 5, and whenever the answer is correct, the horses start to tap, right? And everybody started clapping. Oh, the horse has learned to do some basic arithmetic, and it got famous. So people have started to do experiment on the horse, what he has learned, and he has actually learned to do the arithmetic. And they tried with different arithmetic problem, and every time the horse was doing the right job. So what they do? So horse learn how to do the arithmetic, but what they do now to just do the experiment whether it has actually learned to do the arithmetic or not. So they put a mask on the owner. So that when he points the finger what is 2 plus 2, right? And they started showing the finger, and they hide their faces with the mask. Then horse cannot see the facial expression or the body language, right? And whenever he started 1, 2, 3, 4, they started waiting when the horse will start doing things, and it was not doing things. So the horse has learned to read the sentiment of the people, rather than learning the actual algorithm or the basic mathematics. So it was doing the right job, but it was not doing as it was expected to do. So it has learned the body language of the audience. Yeah. So that's why the name of the project is Clever Hans. So our machine learning model seems like it is doing the correct job. It is just to verify whether it is doing the same way as we human do or not. Okay, so we are going to do a short, not demo exactly, but just showcase how we are going to use this Clever Hans library to generate examples and do the training. So the demo will include we will first train a model, right? Then we do the accuracy on a clean data set. Then we calculate the accuracy on the adversarial data set. Then we will generate some adversarial examples. Okay. So the examples will be like this, how we are going to do this, generate this. So this is just Jupyter Notebook. So first what I'm doing is I'm just using Clever Hans library to import some of the things. We will explain later what we are using now. So this is just setting up the TensorFlow, everything. So how many of you know about MNIST? Just MNIST. Everybody's right. So it's the data set that contains 60,000 samples of numbers 0 to 9. Okay. And how many of you know about fashion MNIST? Oh, nice. So it has just 10, again, similar to MNIST, it has 10 categories of data that has, and the images are of dress, like bags, shoes, t-shirts, something like that. And here we have the categories, right? So for this demo, we are going to use this fashion MNIST dataset to generate the adversarial example. So this is just a boilerplate code that reads fashion F. Okay, so this point we define the Keras model, and these these are the parameters we are going to use for the FSGM, fast gradient sign method, right? So this is like, you just instantiate the object of a fast gradient method, right? So, and these are the parameters, the epsilon. Okay. So this part, just everybody knows that like we have to do these things, right? So what we are going to do, we are going to train a model, right, with the y true and x train and y train. Everything is clean. So we started the training, and these are the logs. So we will stop here. So we can see like when we train the fashion MNIST model, we get the legitimate example accuracy of 90%. And the model has learned to classify the image into correct labels with accuracy of 90%. Right? But with the adversarial example, the accuracy was 0.06. That means like out of 100 adversarial examples, it was classifying only 6 images as the correct label. Right. Okay. So we'll just move forward and see like how we generate the adversarial example. So this is just a very small wrapper I have written to just generate examples. So we will take the Keras model, and we have the attack algorithm and just the keyword arguments. Okay. Just moving forward, this is a code for plotting. So this we have already seen. So fast gradient sign method params and now we will start with this. So this is an image of bag. When we apply this algorithm, fast gradient sign method, we get an image like this. And the classifier has classified this bag as a shirt. So it's the original size of the image is 28 cross 28, so although it's very bad. Yeah. This was the t-shirt top, which was classified as a shirt, which are closed by the way. Ankle boots and shirt. So usually they look similar, but they are classified as a wrong label, right? And we have used the algorithms fast gradient method here in this case. Now comes the spatial transformation method. This is another method to generate adversarial example. What does it do? So these methods, these change the pixel values of the original image, right? But the spatial transformation methods, it just misplace the pixel in a different position. For example, you have like a right angle position, it will just turn it. It spatially transform the image in a different angle such that the model the model will assume that it is a different image or different class. So the first image is browser, yes. When we transform it a little, it classifies it as a bag. This is a pullover, again it's a bag, dress, and this is again a bag. Code and code is a bag. And spatial transformation, and these are like the actual use cases whenever you expose your machine learning model to users, and these are the like valid use cases, right? They look the same, but they're classified as a wrong label. This is another algorithm, projected gradient descent. So it again based on it just modifies the pixel values. So we generated adversarial example using this. This was then just pullover, shirt, bag, and it is a standard for the classifier. So we have a default also algorithm, but it takes ages to run, so I will skip it. Okay. Going back. So generating those adversarial examples was very simple, just to use a particular library, Runs. It gives us a nice interface, and you can just use it on the fly. And because whenever you go through a research paper, what happens most of the time that all the script is cryptic notation we fail to understand and we cannot implement it, right? So this is like a cool thing I would say to help researchers to move forward the frontier of research. Anyway, so coming back to the problem, so what was the culprit behind all this madness? Why the classifier was predicting the class which was not expected, right? Deep models are too linear. So, maybe some may assume like I'm a fool who says like deep models are too linear, right? Deep models are supposed to be non-linear. They have the capability to generate any kind of hyperplane, right? So, but if you clearly see, so this is like in an adversarial example, we have a x bar is equal to x plus eta, so, and this is the noise, so right? And what happens when we take the dot product, like let's assume we are talking about a very simple, let's say, logistic regression model, and we have the output this, right? If we do the multiplication of weight vectors with the input. So by this amount, our activation, not activation, the dot product has changed, right? And we pass this to the activation function. So it all depends on the activation function we are using. So what activation function normally we use? We use rectified linear unit, right? Value. And what happens? So this is rectified linear unit, and it's linear after x is positive, right? Or the input is positive. So in this case, so how much based on the dimension of the input parameter, it grows linearly with the dimension, right? And when we pass this through the activation function, and these are the values we get, right? So just to exploit this point, we have a lot of algorithms that do the gradient with the gradient of the loss function with respect to input, modify the input, and the model is full. So yeah, this was the reason behind it. So in all the examples that I've showed already, so they all use model parameters, right? So what if, like, if I have exposed a machine learning system that is exposed as a service, like kind of an API, right? Then the attacker, like one who is trying to fool the model, doesn't have the model parameter access, and he cannot calculate the gradient, and then he cannot create the adversarial example for that deployed machine learning model, right? So, if you have an idea, like, then why it is a threat? Yeah.
They showed that Tesla cars accidentally turned on their wipers just by showing some white noise in front of the windscreen,
yeah,
for example. And that's a huge threat for autonomous driving.
Exactly. Yes, so I will just come to your point later. So deep networks show a property of transferability. What does it mean? So we have on the y-axis we have the source machine learning models. So for each machine learning model, starting with this KNN, decision tree, SVM, and DNN. So for example, what we have done, we have 100 adversarial example for fooling this machine learning models. For example, for the DNN, deep neural networks, we have 100 samples that fool that source model. And if we apply those adversarial examples that use this source deep neural network models, that fooled another DNN that was trained altogether differently, right? So this is the matrix, like how these properties are transferred to the another model. So what does it essentially mean? That if we train a model A and we have a model B, and if we find an example that fools the model A, it is most likely that it's going to fool the another model B. So this is known as the property of transferability, and this is across machine learning models. So you can see, like, DNN example was able to fool that 79% of the decision tree example was.
Did it also fool humans?
Examples that.
But it doesn't include human.
Okay.
Okay, so just to give you an example, so what is how this is going to use. So for example, this is a remote ML model that is used. So this is a stop sign, and this is the cloud-based service, and we have the output, right? So this is that. He uses his let's say local machine to generate an adversarial example, modifies it, and feed it to the system, right? Even though it looks like a stop signal, but it turns out that the model outputs as the message 300, right? So it's in a full the deployed system. So what we can do to avoid all these adversarial attacks to the machine learning. So one way to do is just include the adversarial examples to your training module, right? So if you include the adversarial examples to the training, then the weights are going to learn, right? And they will not be fooled, right? So this is the equation how we are going to use how we are going to do adversarial training. So what we have done here, so we have this alpha parameter. So for each image we are going to generate a clean image and the adversarial image of that clean image, right? So we can just define alpha is equal to 0.5. So, and we have this loss function with respect to clean input, and we have a, you can see this is not a clean image, and this is the adversarial image that we have derived earlier. And this is again the gradient of the loss function with respect to x, right? And we just add it. So this is will be the modified loss function. And if we train this, train the model using this loss function, maybe our adversarial model is our trained model is foolproof to the adversarial attacks. So we just go to the adversarial training. So what we have done here, this is just the equivalent code for that equation. Here what we have written. So here you can see. So first we have the original image, then we generate the adversarial example, then we create the prediction, and we do the cross entropy calculation for the generated prediction, right? And we just do that for 0.5, and we return the loss. And if we do training using this adversarial loss, this is again we have defined the model parameters and everything, and we started training. And if we continue to training, and what do we see here? So the test accuracy on the legitimate example is 90%, and on the adversarial example 89%. So the model was able to learn like the attacks, right? So this is how we can one way to avoid adversarial attacks. Okay. So this is known as the adversarial training, where you modify your loss function, and we come to the another defense algorithm, which is known as defensive distillation. So if you keep track of this thing, so what are we using to generate the adversarial example? The gradient with respect to the input, right? So what if we make a model that gives you gradient which is not meaningful? Right, then the attacker cannot use the gradient, and he cannot generate the adversarial example. And this is what defensive distillation do. So you train a model. Normally, what you do, then instead of using the hard output training labels, you do the training labels as the probabilities predicted by the previously trained model, and you do the training. It's a very simple thing. So we will initially train a model, then we'll use the output of this model to train another model, and that's what does it bring to the table. It gives the gradient which are not meaningful, and this way it avoids the attack. So what is the fundamental flaw of this algorithm? The user cannot generate an adversarial example, right? But they showed transferability property, right? So yes, all those two things create adversarial training and defensive distillation, and there are many more algorithms that do the gradient masking. So the term gradient masking is used for the defense mechanism that tries to minimize the effect of gradient with respect to input. Yes. See, in all those two, in the first adversarial training, we include that adversarial example already. In the second case, in the defensive distillation, we indicate that gradients are meaningful. So how do we attack a model that is using defensive distillation? So as we already know that deep neural networks show the property of transferability, right? We can train another model and generate the adversarial example using the gradient of this surrogate model, another model, right? And the model with this defensive distillation is prone to adversarial example. It just avoids, it doesn't give you access to create the adversarial example. Okay. And what are the indirect methods? So these two methods are based on the fact that we are going to use the gradient to generate the adversarial example. So there should be a way where we develop a model that doesn't depend on the gradient thing. It should make the model robust by some other properties. So this is like the recent papers, logic pairing, level smoothing, and logic. These two papers are still in review for this conference, ICLR 2019, and this logic pairing was published in 2019, very soon. What it does, it adds another regularization thing. So what it is, so this is a coefficient of L, how you're going to, so it takes two things. First, for a clean image and at the adversarial example. Then it defines like how these two images are close, and that's how they learn. For example, when we train the adversarial example, we know these two images are close, although their pixel values are different, but we can define a parameter that knows like these two images are similar, and we do the training, and we the model trained with using this this loss function has a good defense against the adversarial attack. And these are known as the indirect methods. So we will just talk about the cybersecurity perspective. So everybody knows where this is. So improvise, adapt, and overcome. So first thing is know your adversary. For example, any service you develop that uses machine learning, just know like what are the exploit points of your machine learning, the model you have deployed. Then just be proactive. It's the opposite of being reactive. Just don't wait for someone to attack your model. And for example, if you know like you have deployed some service that does image classification and do some moderation on top of that, just know like what can be the adversaries for your example, and just proactively do it and protect yourself. That means like continuously improve your system. And yeah. So for example, if you have two models to deploy and they have some properties, so how, if you just keep in mind the cybersecurity perspective, so how we are going to choose between two models that have the same let's say accuracy, right? So the one that has low confidence on mistake. Like for example, if we have an adversarial attack, if it is like for example a human, it classifies as a bird, right? But the confidence of that bird was very low. So this model is better, right? It doesn't say that it is a bird with a high confidence. Although, so this way we can infer that although the model is classifying it wrong, but it has low confidence on the wrong prediction. Again, whose mistakes are harder to find. And again, making the model stochastic, that it doesn't repeat the same mistake again and again on the same mistake. Right? Again, the model that is hard to reverse engineer with probes, that means like the attacks. And it is less prone to transfer from related models. So this can be like the criteria to select model. If you have two models and one is better than the other in terms of in the aspect of cybersecurity. And yeah, that's it. And these are all the references that I use to make this presentation. And yeah, that's it.
Thank you. It was very interesting. So, I found it very interesting that you consider spatial transformations as an adversarial attack. I mean, the only place where this makes sense to me is captures, which I suppose is the point. But why do you think of them as adversarial attacks? Isn't it just a generalization of the images? The spatial transformations that you showed in your notebook, you had basically things that were twisted or moved. Sorry, not even twisted, just rotated or moved.
Exactly.
Why is this an attack at all? Isn't it just a generalization of the data?
So it is an attack where, like, if I have the aspect of the image in the original image is fixed, like if I change the ratio, like the proportion, it should still classify the human as a human, right?
Yeah.
Right. So, but the model was not didn't generalize this. So this is also an attack. For example, if I have let's say a human of the aspect ratio that has 90% of the human, and I have the same image that is squeezed to have the 40% proportion of the image, it is still a human, right? But the model doesn't classify this as a human, so this is a kind of an attack. By attack I mean like the model didn't learn the way humans do.
Yeah, but I guess my point is it's not intentional, so
Mhm.
I don't see it as an attack, but maybe.
It is not intentional, but this can happen, right? For example, the stop sign, right? So it can have various sizes. So for example, if you're driving in, let's say, in Italy, if there's a big stop sign, in Germany it's a small. So it should, the stop sign is a stop sign, right? So this can be exploited or maybe very bad for our automatic system.
Does this model deal with watermarks, for example? I mean, how is it helpful?
So
Like hidden sort of really hidden icons, stuff like that.
yes, exactly. So these are not all prone. So it's a normal model that doesn't use the
Let's say you label a shoe with airplane, figure it out.
So you are saying like then I watermark it with something,
Something else.
and it should still classify the original image correctly, right?
Yeah, have you tried that?
So it's the same as like treating the noise. If your training data set has these kind of samples, like in higher proportion, then your model will generalize to learn. But if your training data doesn't have, it will not generalize it, and it will eventually make mistake. Yes.
Yeah, and have you tried methods like sharpening the image and different type of tests to improve the quality of predictions without jumping into
Yeah. So what you're talking about is like you augment your data set, right? You can crop it and you can reshape it and just train the model, but still the gradient is still valid, right? You can find adversary for the model you trained with the augmented data. So these holds true even for that.
without
Yes.
using the algorithms to enhance it. Have you tried using the existing model, like just doing some pre-processing on the images, A/B testing?
I'm not exactly we didn't try, but what I understood, like it's the same as like having less images in your data set or more. Just the same, and they will again be prone to the attacks.
Well, thank you very much for the interesting talk. Have you considered, I mean, also, I really like the notion of the previous speaker saying that, you know, how humans learn. I mean, there are pictures for humans as well, right? Where some see a duck, some see a rabbit. So apparently there are also images that are not clear to humans.
Yeah.
Are they clear to the machines then? And have you looked into what makes us humans put something in the wrong category?
So you're talking about the adversary where human was also confused, right?
Or where humans get confused but the machines don't. I mean, do we have different systems in our human brains and in the machines, so to say?
It totally depends, because whenever we have a trained data, label data, and this data comes from the human. Right? So it totally depends. What you're saying might be true. Yes.
But are there data that the humans labeled? I mean, 50% of the humans labeled this and 50% of the humans labeled that. I mean, it's your lower limit, right? I mean, if you give it to 10 humans, do they all label the same?
The thing is, you have to establish the ground truth, right? Like what the image is. If you are confused, then what is the correct answer? No one knows, right? And it's gonna generalize one over another, definitely.
Yeah, but I mean, you can't expect the machine to be better than a bunch of humans, right? That would be a lower bound.
So how do you define better? Then you have the relative thing, right?
You
But you say like
take 1,000 images, right? You
Yes.
let 10 humans look at them.
yes.
And some labels will be ambiguous, right? You can't expect the machine to be better
So
than that.
let's assume like 5 of them like labeled as B and the other 5 as B. Now A and B, right? And
Exactly.
the humans say, 5 humans say A, 5 humans say B.
Yeah.
Then what is the correct? No one knows. Then we cannot define better if we don't have the baseline.
Exactly, that would be the baseline, right? Well, discuss later.
Yeah.
Sorry, in terms of to deal with the commercial examples, what's wrong with the following idea? That instead of passing the direct image into the model, you apply some denoise filter to get rid of the noise and then pass it to the model. The way to do the same trick to deal with the adversarial example, but most of the examples are shown as to add some noise based on the bottom.
So you are saying that we should add a pre-process stage where we denoise the image.
Yeah.
Then we can
What happens?
So when you deploy a system into real world system, you don't have the control on the input, right?
Yeah, but after you get the input, you can have a certain, let's say, caution filter to filter out the noise. then we have it to the network. So that in that case, all the high frequency knowledge is filtered out of information.
Yeah. Applying caution is just a kind of a normalization action, right? And for example, whenever we train neural networks, so one of the layers can also learn to normalize the image. So just think what you're talking about. You can be explicit about it, but the model internally does it by itself. So even though applying these kind of denoising layers or let's say functions will not help. So this is right and it failed.
I have a small question. So you said that one of the reasons that these models fail was due to rating variation.
Sorry, I didn't understand.
Yeah, so you said that one of the reasons that these models fail is, for example, is due to rating.
Yes, correct.
Yeah, but like, but if you train with adversarial, like cost function, change the cost function, the same model will basically give better performance.
Yes.
So I couldn't understand how training.
Yes, exactly. So we define the loss function as the clean image and the adversarial example also, right? So this is kind of augmenting our the adversarial thing, right? Now this model learns this pattern, like okay, so this whenever I encounter this image and my weights are trained accordingly. So you can think of this as like all the adversarial examples were included in the data set.
So basically, the decision boundary has not too much. The decision boundary has a lot of it's like
So it will modify, it will assume that it has the adversarial examples also. It's kind of just augmenting the data set with the adversarial examples.